Hey y'all, welcome back. On tonight's homework, we're going to be working through some related rate problems, and then we'll get into just some mixed AP practice. Number one says, a ladder of length 8 meters is leaning against the side of a house, and you are at the top of the ladder painting the wall. Unfortunately, the base of the ladder is slipping away from the house at a rate of 1/2 meter per second. How fast are you falling downward when the base of the ladder is 3 meters from the house? So anytime we've got like this geometric setup, I think it's a good idea to sketch out exactly what's happening. So here's the house, here's the ground, here's the ladder. And I'm not much of an artist, but this will do. Okay, we've got a right angle, so we've got a right triangle. The length of the ladder is 8 meters. Okay, and with these ladder problems, you're going to be using the Pythagorean theorem, which is a theorem that relates all three sides of a right triangle. So we've got our x, our y, and then what we'll call our r, which is the hypotenuse. So yeah, the length of the ladder is 8 meters, and the base of the ladder is slipping away from the house at a rate of 0.5 meters per second. So the fact that it's slipping away from the house at a rate of 0.5 or 1/2 meters per second, that's going to give us the change in x with respect to y. In other words, that's going to be our dx dt. How fast are you falling downward when the base of the ladder is 3 meters from the house? So the base of the ladder being 3 meters away from the house is giving us our x value. And what the question's asking is, how far are you falling downward? So really what the question's asking is, what is the rate of change of y with respect to t? In other words, how is y changing? So we'll start off with, like I said, an equation that relates all three of these values, x, y, and r, and that's Pythagorean theorem. X squared plus y squared equals r squared. And we can implicitly differentiate this with respect to t by differentiating each term, like I said, with respect to t, not with respect to x or y. So for each one of these variables, we'll have to do a little chain rule to find the derivative. So for the derivative of x squared is going to be 2x, and if we're differentiating with respect to time, in other words, we're doing derivative with respect to time on each variable, it's going to be 2x dx dt plus 2y dy dt equals 2r dr dt. Notice that the derivative is basically the same on each one of these, except because of the chain rule and because we're differentiating with respect to t, we have this like dx dt or dy dt. And what those represent are the change of that variable with respect to time. So now we're just going to fill in everything that we know and solve for that dy dt. This is going to be what we're looking for, that change in y. So right now we know that the ladder is 3 meters away from the house. So we've got 2 times 3 times the rate at which the ladder is slipping away from the house. And it's slipping away at a rate of 1/2 meter per second. So this is going to be 1/2. Plus 2 times the y value. So we'll just leave that as y for now. Times dy dt. This is really what we're looking for. Equals 2 times the length of the ladder here, which we said was 8, times the rate of change of the size of the ladder. Now, the ladder is a fixed length. It's not going to be changing. So the change in the length of the ladder with respect to time is just going to be 0. So notice that we've got everything plugged in here, and there's really just one variable that we're missing, and that's y. But we can actually find y by going back to the Pythagorean theorem. Notice we've got a right triangle here with a leg length of 3, a missing leg length, and a hypotenuse of 8. So I'm just going to resketch that over here. We've got 3, 8, and our y. So we can use a little Pythagorean theorem here. 3 squared plus y squared equals 8 squared to find the height that the ladder is off the ground at this moment. So 8 squared, 64. 3 squared is 9. 64 minus 9 is going to be 55. And then so y is going to be the square root of 55. Now, algebraically, yeah, you'd put plus or minus here. But because we're talking about, because this number is intended to represent the height that the ladder is off the ground, it doesn't really make sense for that number to be negative. So now I'm going to go back and fill in that number for y. Okay, at this point, we're just going to do a little algebraic manipulation. We're going to rearrange this equation a little bit, do some arithmetic along the way, and try to isolate that dy dt. So 2 times 8 times 0 is just going to be 0. So we have 0 on the right-hand side. On the left-hand side, we've got 2 times 3 times a half. Well, 2 times a half is 1, so that's just 3 plus 2 root 55 dy dt equals 0. So subtracting 3 on both sides is going to give me 2 root 55 dy dt equals 0. And then nope, not equals 0, equals negative 3. And then let me try to move all this other stuff so we're not so crammed in here. Oh, that's about as far as I can go. And then we just need to divide both sides by 2 root 55. Now we should be expecting a negative value here because the height that the ladder is off the ground is getting smaller, right? Because as the base of the ladder moves this way, the top of the ladder is moving down. So away from the wall is going to be the positive direction. Going down towards the ground in the y, that's going to be negative. So the fact that we got a negative number here seems pretty good. And that's going to be our answer. Negative 3 over 2 root 55 meters per second. Number 2 says if x squared plus 3xy minus 4y equals negative 2, determine dx dt. This is what we're trying to find, given that x equals 2, y equals negative 3, and dy dt equals 2. So first what we're going to do is differentiate both sides of the equation here with respect to t. So we're going to have like d dt of that whole equation. And we'll do each one individually here. I'll try to color code as we go so you can kind of see what happens with each term. So first, we'll start with this x squared. We're going to differentiate that with respect to time. The derivative of x squared is just 2x. And then using the chain rule, we need to, we get dx dt, the derivative of x with respect to t. Okay, with the second term, this 3xy, we're going to have to use the product rule. We have 3x times y. Just a little reminder of the product rule. If you want to find the derivative of a product of two functions, it's going to be the derivative of the first times the second plus the first times the derivative of the second, f prime g plus f g prime. Where here, my f would be 3x, my g is y. So the derivative of 3x with respect to t, again, all these are going to be with respect to t, so we're going to end up with that either dx dt or dy dt on each one, depending on what we have. So the derivative of 3x is just going to be 3 dx dt. Okay, that's just this part right here, the f prime, and then times y plus, now we're going to do fg prime, so 3x times the derivative of y with respect to t. All right, so the next term is negative 4y. And so the derivative of that is just going to be negative 4 times the derivative of y with respect to t. So I'm actually going to change this plus to a minus. So minus 4 times dy dt. And then the derivative of negative 2 is just 0, so it's just going to be 0. Okay, so again, what we're trying to find here is dx dt. That's this one. So we're going to have to do a little algebra to isolate that. But basically, we want to keep the terms that have dx dt on the left side, move all the terms that don't on the right side. We're going to have to factor out the dx dt's and the dy dt's as GCFs. I'm going to try to do both of those steps at once here. So please reach out if you're confused about what I'm about to show you. But let's start with the dx dt's that we're going to leave on the left-hand side. So basically, we've got two terms here. We've got this one, and we've got this one. And we're going to leave those over on the left-hand side. Simultaneously, I'm going to factor out the dx dt as a GCF. So I'm going to write it like this. dx dt times 2x plus 3y. And then I'm going to move the other two terms to the right-hand side because they do not have a dx dt. Okay, now I really don't need to necessarily factor out the dy dt, but I think it'll look kind of nice if I do. So I'm going to factor out that dy dt, and I'll have 4 minus 3x. All right, lastly, we need to isolate that dx dt. That's what we're trying to find, right? Let's keep track of that. We're going to divide both sides by 2x plus 3. So we have this dy dt times 4 minus 3x over 2x plus 3y. Now, hopefully, they gave us everything we need to find dx dt, and I'm looking back at the problem. It looks like they did. We've got x equals 2. Okay, so that's going to go here and here. We've got x equals y. So that's going to go right here. And finally, we've got the dy dt, which is going to go here. So we don't have any like missing variables or anything. It's just going to be a matter of plugging in those numbers in the right spot and then simplifying. So dx dt will be 2 times 4 minus 3 times 2 over 2 times 2 plus 3 times negative 3. So yeah, let's simplify this a little bit. 3 times 2 is 6. 4 minus 6 is negative 2. So we get 2 times negative 2. On the denominator side here, we have 4 minus 9. So that's going to be negative 4 over negative 5. dx dt is 4/5. Number 3 says a screensaver on a computer screen shows a circle that starts as a dot and expands outwards. At the instant that the circle has an area of 81 pi centimeters squared, so that seems like that's going to be important. The radius of the radius is increasing at a rate of 3/2 centimeters per second. Okay, find the rate at which the area of the circle is changing at that instant. So the formula that we're going to be working with here is area of a circle. So area of a circle is pi r squared. And if we differentiate that with respect to t, we're going to get dA dt equals, pi is just a constant here. So we've got 2 pi r dr dt. And so what's given is the rate at which that the radius is increasing. Okay, so this is my dr dt right here. The area is 81 pi. And so we're looking for, what are we looking for? The rate at which the area is changing at that instant. So yeah, we're looking for, find the rate at which the area is changing. So the question here is, what is dA dt? So we're going to fill in what we know. Excuse me. We're going to fill in all the variables that we know. There is one that's sort of outstanding here that we don't know yet, but we'll go and we'll figure that out. The dA dt, that is what we're trying to find. So we have 2 pi times the radius, which we haven't figured out yet. That wasn't explicitly given, although we will go back and find that, times 3/2 for the dr dt. So the question about the radius is like, what is the radius? They didn't say explicitly what the radius was, but it does say the area is 81 pi. And so if the area is 81 pi and the area is pi r squared, we can determine pretty easily that the radius at this moment is 9. So now we just need to simplify this answer here. We've got 2 divided by 2, that's just 1. So we have 9 times 3 is 27. And so we get 27 pi, and we do want to throw in the units there. Since dA dt is talking about the rate at which the area changes, that's going to be the area centimeters squared per time unit, which is seconds. Oh, forgot the pi in there. All right, and there's number 3. Let's take a look at number 4. A spherical balloon is being inflated at a rate of 3 cubic inches per second. What is the rate of change of the radius of the balloon when the balloon's radius is 5 inches? And then they give us the volume of a sphere. Now, on the AP test, they're going to give you this volume of the sphere formula, so you don't need to worry about memorizing that. But that's where we're going to begin. V equals 4/3 pi r cubed. If we differentiate that with respect to time, we're going to get dV dt equals 4 pi r squared dr dt. Now in this problem, it says that it's being inflated at a rate of 3 cubic inches per second. So that's the dV. This rate of 3 cubic inches per second, that is describing how the volume is changing over time. And then it says the radius is 5 inches. That's going to be our r. And so we're looking for what is the rate of change of the radius. So it's saying how is the radius changing with respect to time? We're solving for dr dt. So this fraction right here, or this differential, I should say. So dV dt, we're going to plug in 3. And then for the radius, we're going to plug in 5. And now we're just going to do a little bit of algebraic manipulation to get that dr dt. So 5 squared is 25. 25 times 4 is 100. So we get 3 equals 100 pi dr dt. So we just need to divide both sides by 100 pi. So dr dt is 3 over 100 pi inches per second. But none of the answer choices are written like this. So this particular question, if the answer choices are written like this, you're not going to be expected to actually divide by 100 pi by hand. This is going to be done with a calculator. And so I'm just going to type that out off to the side. Now you're going to have access to Desmos, so it shouldn't be too much trouble, hopefully, to actually type that in. So let's see, 3 over 100 pi is 0.009, which would round up. Looks like they're rounding because it's really like 0.95. Round up to 0.010. So in the multiple choice section on the calculator, multiple choice, they're always going to round versus truncating. So you just want to be ready for that. I know throughout the year, I've been trying to train you to just truncate everything because on the free response, I don't want you to make any errors because you rounded incorrectly, and they do accept truncation. So, this is a little different on the multiple choice. You just got to be ready to round your answer rather than to truncate it. Number 5, a hemispherical water tank. So first of all, hemispherical, this is like half of a sphere. Okay, so it's like the bottom half of a sphere. It has radius of 6 meters long and is losing water. So we got the radius right here is 6. It's losing water, so we're expecting a negative rate of change for that volume. The area of the surface of of the water is 12 pi h minus pi h squared square centimeters. Okay, so basically what it's talking about is the area of this, okay, is going to be that 12 pi h minus pi h squared square meters, where h is the depth in meters of the water of the tank. So when h equals 3 meters, I don't really like how this got formatted here. The h equals 3 got cut off. But the depth of the water is decreasing. So depth of the water, so that's going to be basically the height, is decreasing at a half meter per minute. So the dh dt, the change in the height or the depth of the water, is decreasing at a rate of 1/2 meter per minute. So it's going to be negative 1/2. At that instant, what is the rate at which the area, sorry about that. At that instant, what is the rate at which the area of the water surface is decreasing with respect to time? So we're looking for the rate at which the area is decreasing. So we're looking for the dA dt. So you actually don't need the volume formula here, I don't think. It's not really talking about volume, it's talking about the area of the base. So that's going to be this equation that they gave us initially, 12 pi h minus pi h squared. Let's go ahead and differentiate that with respect to time. dA dt, that's what we're looking for, equals 12 pi times dH dt minus 2 pi h dH dt. And so the dH dt is given right here. It's negative 1/2. So we'll plug that in here and here. And then the height at that time, what was it? It was 3 meters. So we're going to plug that in here. So this is going to be 12 times pi. The dH dt was negative 1/2 minus 2 pi times the height, which is 3, times dH dt again is negative 1/2. So now we just need to simplify this, and then we should have our answer. So negative 1/2, negative half of 12 is going to be negative 6 pi. Then over here we've got half of 2 is just 1. Negative times negative is positive. So we have plus 3 pi. Again with the bells here. So we get negative 6 pi plus 3 pi is going to be negative 3 pi. Now the question's asking, what is the rate at which it's decreasing? So the fact that this is negative means it's decreasing, okay, at 3 pi meters per minute. So our answer here is A. Number 6, a circular oil slick of uniform thickness contains 100 cubic centimeters of oil. The volume of oil remains constant. Okay, so it's a circular oil slick, uniform thickness. So basically, we've got like this circle with a little bit of thickness. So really what we have is this real like short, I don't want to draw this, short cylinder, something like this. Okay, so we have the volume. Volume of the oil remains constant. As the oil spreads, the thickness is decreasing at a rate of, so the thickness being like the height is decreasing at a rate of 0.01 centimeters per minute. That's going to be our dH dt, but be careful because it's decreasing, so we're going to call it negative 0.01. At what rate is the radius of the slick changing? So the rate of the radius is going to be our dr dt, and the diameter is 20 centimeters. Now our formula is going to be in terms of the radius. So the diameter being 20 means that the radius has to be 10. So the diameter is twice the radius. Okay, so volume of a cylinder is pi r squared times the height. And we'll have to use the product rule to differentiate this. Just a little reminder, I think we wrote it earlier, but if we want to find the derivative of a product, we find the derivative of the first function times the second, plus the first function times the derivative of the second. So in this case, the first function being pi r squared and the second function being h. So our f prime here would be 2 pi r times dr dt, then our g is h, plus the first function, pi r squared, times the derivative of the second, which would be dh dt. And what we're looking for here is the dr dt. We're looking for this one. So hopefully we can fill out everything else. Now it says the volume of the oil remains constant. And so when something remains constant, that means its rate of change is 0. Imagine you have a constant function that's just a horizontal line. It has a slope of 0. So anytime you've got a constant value, then its rate of change will be 0. So the dv dt is 0 because the volume is not changing. The radius is changing. Okay, currently the radius is 10 because it said the diameter was 20. The dr dt, that's what we're trying to solve for. The height, do we have the height? I don't think the height's given here, is it? Yeah, the height's not given, so we're going to have to find that out to the side. So over here to the side, I'll do a little scratch work here. If the volume is pi r squared times the height, what we need is the height. We know the volume is 100 cubic centimeters of oil. The radius at that time is 10. So that should give us the height. Oops, that should not be equals the height, but times the height. So 10 squared is 100. So if we divide both sides by 100, we get 1 equals pi times the height. So the height is 1 divided by pi. Plus pi times the radius, which we already established was 10, squared dh dt is at negative 1/100th. Okay, so let's see how much of this we can simplify. So yeah, we've got 0 equals, we've got 10, so we've got pi times 1 over pi, so that those will reduce to 1. Right? Pi divided by pi is just 1. 2 times 10 is 20. So we've got 20 times the dr dt that we want, plus we got 100 times negative 1/100th. 0.01 is 1/100th. If we multiply that by 100, we're just going to get 1. So we have actually minus pi here. All right, these two will effectively, I don't want to say cancel out, but they will reduce to 1. Okay, so if I'm solving for dr dt, I'm going to add pi and then divide by 20. So dr dt is going to be pi over 20. That's going to be our answer. And the units here will be in centimeters per minute. All right, so that's enough related rates problems. Now, I mean, if that's all you're here for, you can go ahead and click off the video here. But after that, we're going to just go through some mixed AP practice. Some of these might require a calculator, not all of them. We'll just kind of pull up the Desmos calculator when we're ready for it, when we need it. But otherwise, we're going to try to do as much of this by hand as we can. Okay, so number 7, we got a little bit of limit practice here. Now with limits, there's a couple different ways you can approach these, but anytime your limit, if you try to do direct substitution and you get an indeterminate limit, like let's say you get something divided by 0 or infinity divided by something or something like that, 0 divided by 0, infinity divided by 0, infinity divided by infinity. Did I say 0 over 0? I don't know. But any of those indeterminate forms, you can use L'Hopital's rule. That doesn't mean you have to use L'Hopital's rule. You can, we went at the very beginning of the year, went over some different algebraic techniques for like canceling out, like we did factoring and canceling, or multiply by the conjugate and finding a way to cancel stuff out that way. Basically, whenever you've got a removable discontinuity, you can try to remove it with factoring or some other algebraic technique. But honestly, anytime you got that indeterminate form, sometimes it's just easier to use L'Hopital's rule. So every opportunity that I get here to use L'Hopital's rule, I'm just going to go ahead and use that method instead of using those kind of older methods that we learned in Unit 1. So basically what L'Hopital's rule says, I'll just write it out here. It says that if you have an indeterminate limit, meaning like if you plug in whatever x is approaching and you get something like, so like the limit as x approaches a of, some function, if that equals like 0 over 0 or, like infinity over infinity or something like this, or any indeterminate form, where you can't actually compute it, then what you can do is you can take the derivative of both the top and the bottom and then try direct substitution again. So you're going to differentiate the top and bottom and then try direct substitution again. Okay, if you get another indeterminate form, like let's say you use L'Hopital's rule, and then you get something like 0 over 0, then you can actually just use L'Hopital's rule again. Just go find the second derivative, and if that doesn't work, the third derivative. And you can keep differentiating until you get the expression to a point where you can use direct substitution. So let me show you what I mean by that on A. Like on A, if I try to plug in 5, I'm going to get something divided by 0. Specifically, I'm going to get 0 divided by 0. All right, like if I take this 5 and put it in here, here, I'm going to get 0 over 0. So while you could solve this, you could find this limit by factoring and canceling. And maybe I'll just kind of like briefly go over that. The denominator here is x plus 5 times x minus 5. You got a difference of 2 squares. And then up top, we've got x, what would that be? Plus 7 times x minus 5. Notice how you have an x minus 5 on both the top and the bottom. You could cancel these out and then plug in the 5, in which case you'll get 12 over, what is that? 5 plus 5 is 10, right? So 6 over 5. So you would get that, but you don't have to do the factoring and canceling. If you want to avoid the factor and cancel and use L'Hopital's rule, you can just differentiate the top and the bottom. So the top being 2x plus 2, the bottom being 2x, and now we can try direct substitution, and it turns out we still get 12 over 10. So you have this option of either kind of doing it the old way that we learned before we even knew what derivatives were, but once we learned what derivatives were, we talked about how L'Hopital's rule can kind of be a nice little shortcut for you. So like in part B, for instance, we could use L'Hopital's rule here, right? If I try to plug in 0 over 0, I'm going to get tangent of 0, which is 0, divided by 0. So there's going to be another like 0 over 0 case. So I'm going to try to use L'Hopital's rule here, especially because I don't know that I really have another technique I could use. Maybe I could rewrite tangent as like sine over cosine or do something funny like that. But really, I think we're just going to go with the with L'Hopital's rule. It's probably going to be the most direct way to get there. So the derivative of tangent of pi x, well, the derivative of tangent is secant squared, but we are going to have to do a little chain rule here. So we get secant squared pi x times the derivative of the inside, which is just pi. Okay, over derivative of x is just 1. So notice at this point, we can just go ahead and plug in 0. So if I plug in 0, I get secant squared 0, which is going to be the reciprocal of cosine of 0. Now, cosine of 0 is just 1. So the reciprocal of 1 is 1. So we just get 1 times pi divided by 1 is pi. All right. For part C, we're going to run into a little bit of a problem trying to use L'Hopital's rule, I think, because if I try to plug in, first of all, you can't just plug in infinity. So that's not going to work. Instead, we're going to have to think about the horizontal asymptotes and what are the relative rates of growth of both the numerator and the denominator. So as x goes to infinity, the numerator is going to infinity, so is the denominator, but all exponential functions are going to be growing faster than any polynomial function. So if the denominator is growing faster than the numerator, in other words, if it's bigger on bottom, then the horizontal asymptote, which is also the same as the long-term behavior or the value of the function as x approaches infinity, is just going to be 0. Now for this next one, both the numerator and the denominator are quadratic functions, so they grow at basically the same rate. And so to find the limit as x goes to infinity, or to find the horizontal asymptote of this function, in other words, what is the function's value approaching as x goes to infinity, it's just going to be the ratio of the leading coefficients. So that's going to be 4 over 3. So 0 plus 4 over 3 is going to be 4/3. Okay, number 8 says the function f satisfies f of 0 equals 15. The first derivative of f satisfies the inequality. So basically it's saying the derivatives in between 0 and 10 for all x on the closed interval 0 to 6. Selected values of f prime are shown in the table. The function f has a continuous second derivative for all real numbers. Part A says determine the equation of the line tangent to f of x at x equals 0. Okay, equation of a line, equation of a tangent line. We're going to approach this the same way that we have been since nearly the beginning of the year, which is we're going to find a point, we're going to find a slope, the point being x, f of x, x comma y, and then the slope, of course, being f prime x. Okay, now once we have the point and the slope, we can come up with our tangent line approximation by writing the equation in point slope form, and then we'll just go from there. So the point here is when x is 0. Okay, so when x is 0, y is 15. And if you're wondering, hey, where did that 15 come from? Well, it told us at the beginning of the problem that f of 0 was 15. Now the slope at x equals 0 is 6. Okay, that's the rate of change. That's the value of the derivative. So the slope equals 6. So our equation, our tangent line approximation at x equals 0 is going to be y minus 15 equals 6 times x minus 0. Now we're going to use this to approximate f of 0.03. So we'll say f of 0.03 minus 15 is approximately equal to 6 times 0.3 minus 0. So 0.3 minus 0 is just 0.3. 0.3 times 6 is 1.8. 1.8 plus 15. So I'm kind of doing all those steps in my head here. It's a little dangerous, but I'm going to roll with it. Now, what did I say? 6 times 0.3 was 1.8. 1.8 plus 15 is 16.8. Okay, so that's the approximation. And then on top of that, it says, given that f double prime is positive, now right away, before we go any further, f double prime being positive means that f is concave up. In other words, it's like doing something like this on that interval. So if the function's concave up, then our tangent line approximation, our tangent line is going to be below the curve, meaning that our approximation is going to be an underestimate. Okay, so our estimate is going to be less than f of 0.3. Okay, so the actual value of f of 0.3 is going to be above 16.8. Okay, this estimate is less than the actual value. Okay, and that's because f double prime is positive, meaning that f is concave down. Concave up on the interval 0 to 0.3. Okay, yeah, there's part A. Part B says use the data in the table to approximate the second derivative at 2.5. So the way we're going to approximate the slope of the slope at 2.5 is we're just going to use the slope formula. Okay, we're finding the rate of change of the rate of change. So we're going to say that this is f prime of 3 minus f prime of 2 over 3 minus 2. Okay, so this is going to be the approximation for f double prime of 2.5. Okay, so f prime of 3 is 4, f prime of 2 is 9. 4 minus 9 over 3 minus 2 is going to be negative 5. Part C says use a left Riemann sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of f of 6. So Riemann sums are a method for approximating an integral. And so if we're going from 0 to 6 here, so we say basically like the integral from 0 to 6 of f prime is going to approximately equal f of 6 minus f of 0. So if we're looking for f of 6 and we add f of 0 to both sides, f of 6 will approximately equal, well, actually, no, this would be equal to. We haven't actually done the Riemann sum yet. Integral from 0 to 6, f prime x dx plus f of 0. So this integral right here is what we're going to use the Riemann sum for. We're going to estimate the value of that integral by multiplying the length and heights of different rectangles. So the intervals here are going to be from, it says 3 subintervals of equal length. So one's going to be from 0 to 2, one's going to be from 2 to 4, one's going to be from 4 to 6. So I'm running out of room here, but so f of 6 will be, now we're going to estimate, let's see, so the length of the first interval is 2, and since we're dealing with a left Riemann sum, we're going to grab the left partition's value, so 6 on that first one, 9 on the second one, and then the last rectangle will have a height of 2. And then plus f of 0, which was given initially as 15. So we've got 2 times 6 is 12, plus 18, plus 4, plus 15. That's going to be 30. 30 plus 15 is 45. 45 plus 4 is 49. So our estimate for f of 6 is 49. Part D says evaluate the integral from 2 to 4 of f double prime. All right, so using the fundamental theorem of calculus, we can rewrite this integral of f double prime as f prime 4 minus f prime 2. Let me kind of box this off so I don't get confused on the work here. And both of these values can be found in the table. So this problem ends up being like a lot easier than you might think. F prime of 4 is 2. F prime of 2 is 9. I'm just grabbing those values from the table right here and right here. 2 minus 9 is negative 7. Part E, find the limit as x approaches 0 of f of x minus 15 e to the x over x squared minus 3x. So if I just try to substitute in 0, f of 0 is 15. So I'm going to get 15 minus e to the 0 is just 1. So 15 over 15 over 0 minus 0. So I get a 0 over 0 situation. So I'm going to use L'Hopital's rule, which says that I can rewrite this limit, or basically set it equal to the same limit, but with the derivatives at the top and the bottom. So the derivative at the top is going to be f prime x minus 15 e to the x. E to the x is just its own derivative, divided by 2x minus 3. And now if I try to plug in 0, I won't have as much of a problem. So this is going to equal f prime of 0, which got to go back up to the table, and we see that that's 6. So 6 minus e to the 0 is 1, so just minus 15, over 2 times 0, so it's just 0 minus 3. So 6 minus 15 is negative 9 over negative 3, which equals 3. All right, number 9. For what values of x does this graph have a point of inflection? Okay, so points of inflection occur anytime the second derivative is 0. Well, let me be more specific. A point of inflection occurs when you have a sign change on the second derivative. Okay, in other words, when the concavity changes. Okay, now this can be, like I said, when the second derivative equals 0. It could also happen when the second derivative is undefined. So basically what we're going to find are the critical values of the second derivative and then create a sign chart and make a note of when the sign changes. So first we're going to have to find the second derivative. Y prime is going to be 15x to the 4th plus 40x cubed y double prime then, let's see, 4 times 15, 30 times 2 is 60, x cubed plus 120, x squared. So to find, now this is a polynomial function, so it's not going to be undefined anywhere. We don't need to worry about that. But what we do need to do is find the zeros of this function. So I'm going to set 60x cubed plus 120 x squared equal to 0. Factor out a GCF, which would be 60x squared, leaving me with x plus 2. And that's going to give me two critical, subcritical values, not even critical values. One at x equals 0 and one at x equals -2. So now let's make a number line chart for f double prime with 0 and -2 being partitions for this number line. And we're going to test a number in each of these intervals to see whether the second derivative is positive or negative. We don't really care exactly what it equals. We just want to know if it's positive or negative so that we can identify whether or not there's a sign change there. Now, a little shortcut here is if you know your multiplicity rules, you know that the sign is not going to change if you have an even multiplicity. So as I go through this, I'm not expecting a sign change to happen at 0. I am expecting a sign change to happen at -2 because it doesn't have an even multiplicity. But let's just work it out and make sure that that's correct. So if I plug in a number like -1, I'm going to get a positive times a positive, so that's going to be positive. Oh, what am I doing here? -2 is less than 0. Let's fix that up. So we actually want to pick a number like -3 there. So -3, you're still going to have a positive, but times a negative is actually going to be negative. A number between 0 and -2 would be like -1, which we just tested earlier. We know that's going to be positive. Wait a minute. Oh, yeah. So we do have a sign change at -2, as we expected. I'm not expecting a sign change at 0 for the reasons we said just a minute ago. But if I plug in a number like 10, we can see that this is going to be positive also. So we have a sign change here, but not here. All right, so the only point of inflection here is going to be at -2. And so our answer is B. Okay, moving along to number 10, another multi-step problem. This one says that the graph of f prime, which is the derivative of f, is shown in the figure below. Now, what x value does f have a point of inflection? So a point of inflection occurs when you have a change in concavity. Okay, a change in concavity of f. One way to find this, especially since we're given a graph of f prime, is when the slope of f prime, so the slope of f prime changes sign of f. So when we're looking at this graph, we're looking at the slope of f prime. We're looking for it to change sign. So like, for instance, at q, the slope of f prime is changing from negative to positive, indicating that f double prime is changing from negative to positive. At s, we have the slope changing from being positive to negative, so that is also going to be a point of inflection. And finally, we have one at t. So we have q, s, and t. All those are x values where f of x has a point of inflection. And the reason why we know that to be true is because f prime, or maybe I should say the slope of f prime changes sign. Let's move this over. I'll just rewrite it. Really apologize for my voice kind of going away. I'm going to do the best I can. Hopefully we can get to the end of this homework. So yeah, it's a change of concavity in f. In other words, you're looking for the slope of f prime to change. Okay, part B says, on what intervals is f decreasing? So f will be decreasing anytime f prime is negative, and that's really our justification here.
So if we're looking at the graph, let me erase these little circles and stuff, but f prime is going to be negative below the x-axis. So in other words, like this whole interval here, and I guess that's pretty much it. So the interval is going to be from P to R. And the justification is because the graph of f prime is below the x-axis. Part C, determine all the critical values of f. So first of all, critical values of f are x values where the derivative of f is either 0 or undefined. So either f prime equals 0 or f prime is undefined. Now, based on this graph, it doesn't look like there's anywhere where it's undefined. So we're really just looking for where f prime is 0. We've got one at P, R, and T. All these are critical values, P, R, and T. And so what we have to do next is classify them as being either local max, min, or neither. So if we're thinking about how the graph of f is related to the graph of f prime, if we have a local maximum value, the slope is going to change from positive to negative, meaning like f prime will go from positive to negative. If we have a local minimum, so this is for a max, a local minimum, the slope is going to change from negative to positive. Okay, and so on the graph of f prime, we're going to be looking for the graph to switch signs from being negative to positive, and then we'll have a minimum. The other thing that can happen at a critical value is you have something that maybe does something like this, or it can be a little different. But either way, it's neither a max or a min. In this case, like the slope does not change sign. Okay, now it could be positive, it could be negative to negative, doesn't matter. If the sign's not changing sign, then it's not going to be a local extreme value. So let's go through each one. At P, we have a local or a relative, well, let's see here. It's going from, f prime is going from being positive to being negative. So that means that f, the graph of f is going to do something like this. We've got a local maximum. And the reason for that is because f prime went from being positive to negative. At point R, let me erase all this. Okay, at point R, f prime is going from being negative to being positive. So that means that on the graph of f, we would have a local minimum. So at R, we have a local minimum because f prime went from being negative to positive. Finally, at point T, we would have a critical value there, but notice how the value of the function is negative on the left side. Positive on the left side, positive on the right side. The sign is not going to change from the left and the right side. So here we have neither a max or a min. Okay, neither, because f prime didn't change sign. And at part D, it says on what intervals is the graph concave down? So the graph is going to be concave down anytime the second derivative is negative, meaning the slope of f prime needs to be negative. So if we're looking at this graph, we can see we've got an interval from negative infinity to q, and also from s to t. Both of these intervals have f prime with a negative slope, so you can say that f double prime is negative, therefore it's concave down. So how do we want to write this? We want to say that like the first interval from negative infinity to q but also from s to t, both of these intervals, f is concave down because the slope of f prime is negative. You could also say that f prime is decreasing, would be another way of saying that. So you could either say slope of f prime is 0, or you could say f prime is decreasing. You could also make a similar statement back on letter B, where we said f prime was less than 0. You could also say that f, well, I guess we don't have the graph of f, so we can't say that. So I take that back. Okay, so here we go. That's our answer for part D. And let's move on to number 11. It says a differentiable function has the property that f of 5 equals 3, and f prime, or the slope of f at 5, is 4. What's the estimate for f of 4.8 using the local linear approximation for f at x equals 5? So we're going to come up with a linear approximation. Basically, we're going to come up with an equation of a line that is tangent to the curve of f at x equals 5 and use that to estimate f of 4.8. So the way we set up these linear equations is the same, going back almost to the beginning of the year where we need a point and a slope. I'm not sure why I put slope first there. I usually find the point first. Okay, so the point is going to be at x comma f of x, and the slope is going to be f prime x. So the point that we're going to use at x equals 5 is 5 comma 3. That's given right here. The slope is also given. The slope at 5 is 4. So now we're ready to write the linear equation that we'll use for the approximation. Y minus 3 equals 4 times x minus 5. We're using this to estimate f of 4.8. So we're going to substitute in 4.8 into x and solve for y. So y minus 3 equals 4 times 4.8 minus 0.5, just 5. 4.8 minus 5 is going to be 0.2. 0.2 times 4 is going to be 0.8. And 0.8 plus 3 is going to be 3.8. Nope, hold on. Back it up. 4.8 minus 5 is negative 0.2. So this would be negative 0.8. And then we add 3, it's actually going to be 2.2. So that's what we got for y. Probably a better way of saying this is that based on our approximation, our tangent line, f of 4.8 is approximately 2.2. Number 12, if the derivative of f is f, the derivative of big F is little f for all real numbers f, and k is a constant, then what's the integral from 1 to 2 of f of kx dx? So we are going to use the fundamental theorem of calculus here. Since f is the derivative of, since little f is the derivative of big F, that means big F is the antiderivative of little f. Okay, that's going to come in handy when we actually, try to do this integral here. So using the fundamental theorem of calculus, this will equal the big integral, or the big F rather, of kx. But let's actually back this up. You know what? I think we're going to have to do a u substitution here. Didn't quite catch that at the beginning. But because we do have a composite function here, we're going to let kx be u. All right, so the derivative of that would be k dx, and that would be du. Now we don't have k dx, we just have dx. So if we divide both sides by k, then we can rewrite dx as 1 over k du. All right, now we're looking a little better here. So let's see here. So this is going to equal, like if we try to integrate, maybe I'll just show you this. The antiderivative of f of kx is going to be, let's see, what is that going to be? Let's write that out. So if the integral f of kx dx and we're going to let u be kx, and we're really finding the integral of f of u du times 1 over k. And so the antiderivative of f is little f is big F. So this is going to equal 1 over k big F of u plus c. Now in this case, u is the kx. So we'll have 1 over k. Maybe I should move this up. 1 over k big F of kx plus c. So that's the set of antiderivatives. Now we're ready to, I was trying to get ahead of myself there using that fundamental theorem. So here we've got from 1 to 2, 1 over k times f of k times 2 do I have enough parentheses there? No. Minus 1 over k times f, big F, of k times 1. All right, so let's clean this up a little bit. We've got, here, I'm going to put some brackets on here and make this a little easier to look at. 1 over k times f of 2k minus 1 over k times f of k times 1 is just going to be k. So if I factor out that 1 over k, I'll have f of 2k minus f of k. Yeah, I was not expecting that u substitution at the beginning. But yeah, upon closer inspection, because we have that composite function that we're trying to integrate, that's usually the indication that you want to use a u substitution. It's really just like the opposite of the chain rule. Okay, number 13, last problem here. The figure shows the graphs of the functions f and g. If h of x is f of x times g of x, then what's h prime 2? So first, let's find h prime x, which is going to be the derivative of h. And so if we're trying to differentiate h, we need to use the product rule, since we have f times g. So using the product rule, we're going to have f prime g plus f g prime. So if I want to evaluate h prime of 2, I'm going to need to find the slope of f when x is 2. I'm going to need to find the value of g when x is 2, the value of f when x is 2, and the value of the slope of g when x is 2. So let's start finding these values here. We're going to need first the value of each function at 2. So at 2, g of 2 is 1. And up here we can see that f of 2 is 3. Okay, the slope, since both of these are lines, they're going to have a constant rate of change, meaning we can find the slope by just doing some rise over run. So like this top function, if I just pick 2 points here, you can see that the slope is up 1 over 2. Right? So we can see that f prime at 2, and really f prime at any number, since it's linear, it's going to be constant, is going to be 1/2. On the other hand, g is going, if I pick 2 points here, down 2 over 1, so, sorry, not f, but g prime of 2 is going to be -2. So now we have everything. It's just a matter of plugging everything in. F prime of 2 is 1/2. G of 2 is 1. F of 2 is 3. And g prime of 2 is -2. So we have 1/2 minus 6, which would be, well, as a fraction, it'd be 1 minus 12 is -11 over 2, or if you write it as a decimal, 5.5. Okay, thanks for hanging in there with me. I know it's probably a little hard to understand everything I'm saying here because of my voice, so I really appreciate you taking the time to make sure that you understand all these questions. Hopefully, I did enough to explain these problems, but As always, if you do have further questions, please reach out. I'll be happy to help you. And maybe, in a couple of days, my voice will be back and I can explain these problems a little bit more clearly. So anyway, thanks for watching. Y'all have a great day.